In this video, we're going to discuss our final derivative rule, what we call the chain rule. So this rule is going to allow us to deal with the most complicated functions we're going to see. Now, keep in mind, in many cases, what we think of as a complicated function is actually a composed or a composite function. So what that means, composing functions, that means that one function has essentially been plugged into, substituted into, treated as the input for another function. So you can think of one function as being nested inside of another. So when you see a function that has a lot of operations represented, sometimes you can think of it as a simpler function plugged into another function. And so the nesting of the two functions, one into the other, is what ends up creating a more complicated function from what we can otherwise think of as fairly simple algebraic operations. So the composition of two functions, f and g, is defined in the following way. So the formal notation would be f compose g, which uses a little open circle in the middle. Now keep in mind this looks similar to the symbol for multiplication, but multiplication is a closed dot. An open circle is composition. So f composed with g of x, which literally means we take the function f, think of this as the outside function, and then the input from the function f, where we normally substitute just a constant or maybe some type of algebraic expression. Here we're subbing in the actual function g of x as our input. So the function g of x has been nested inside of the function f as its input. So we're going to practice a little bit with composition before we actually look at the derivative rule, the chain rule. The chain rule is going to allow us to differentiate functions that look like this, where we have one function nested inside of another. Now when you compose functions together, typically you want to start from the inside, start with the inner function, in this case g of x, that nested function, and work your way out. And in general, order matters. So when I say f composed with g, f composed with g is in this particular order. That means f is the outside function and g is the inside function. G composed with f is not the same thing. So in general, f composed with g of x will not be the same as g composed with f of x, except for one very specific case in which they end up being the same. In general, they will not be the same. So we would say that composition is not a commutative operation. Commutativity means you can switch the order and it doesn't change anything. Addition is commutative, multiplication is commutative, subtraction and division are not commutative. You flip the order and it changes things. Composition is also not commutative in general. The order you compose two functions in matters. So just to give you a sense of what's happening when we compose, think of x as being an input for g, and then we're taking the output we get from g of x and making that output as one unit the input for the function f. So if we were to draw sort of a machine to demonstrate how different things are being layered into one another, our inputs, what we're going to think of as x, are being plugged into g. The function g is then taking its rule and applying that rule to whatever our input happens to be. G then outputs its output represented as g of x, and that then becomes the input to the function f. So the function f takes g of x as an input, and g of x took x as an input. So the final output is this nested composed function f of g of x. So we're taking x values, plugging them into our inner function. The inner function is then evaluated with that particular input, and the output from that evaluation is then substituted into the outer function. So you start on the inside and work your way outward. So let's do a couple of function compositions, just practicing with this particular operation of composition. So f of x is defined as x to the fourth power, and g of x is defined as 2 plus x cubed. And based on these two function definitions, we want to find f composed with g of x and g composed with f of x. And as we mentioned before, they're not necessarily commutative, so we're going to compare these two and we'll see if they end up being the same. So f composed with g of x means literally that we're taking the function g of x and we're treating it as one unit as the input for the function f. So what this means is that wherever we see an input for the function f, we're going to substitute in g of x, whatever g of x happens to be. And we can approach this in a couple different ways. The way I like to do this is to go ahead and sub in whatever we know g of x is. So x is being plugged into g. In other words, we're not really doing anything special here. We're not plugging in a specific unique input. But g of x, the only thing we know about that, if we're not subbing in a particular input, is that g of x is equal to 2 plus x cubed. So wherever I see a g of x, I could substitute its function rule, and that's what I'm going to do. So f of g of x would be the same thing as f of whatever g of x is equal to, which is 2 plus x cubed. So what this now means is we're taking the rule for f, which says take an input and raise it to the fourth power, and we're applying it to this specific input, 2 plus x cubed. So f of 2 plus x cubed is going to take this input and it's going to raise it to the fourth power. Now make sure you put parentheses around it when you do that substitution. So 2 plus x cubed is taking the place of x in this function f. Keep in mind we're using f, not g. Make sure you pay attention to which rule you're using. But we're making that the input and we're raising it to the fourth power. Now simplifying that, this is not the same thing as 2 raised to the fourth power and x cubed raised to the fourth power. Remember, an exponent means repeated multiplication, so this would literally be this binomial multiplied by itself 4 times. And unfortunately, that would be a nightmare to simplify by hand. So we're just going to leave this by itself just as is. We're not going to go any further with that. So that would be the result of our composition. That would be the composite, the composed function that results from f composed with g. Now what if we take the same functions but compose them in the opposite order? So g composed with f would take the function f of x and would make it the input for the function g. So again, x is being plugged into f, and then the output of that function evaluation is then being plugged into the function g. So f of x, we don't know anything about it specifically because we don't have a specific value for x. All we know about f of x is that it is the same thing as x to the fourth power. That's its function rule. So g of f of x could be rewritten as g of x to the fourth, since that's the same thing as f of x. So g of x to the fourth means I'm going to take the rule for g, and wherever I see a generic input, I'm going to replace it with this specific input, x to the fourth. So g tells me to take 2 as a constant, add on my input cubed. Here my input is x to the fourth power, so I'm then cubing that. Now I can simplify this, a power raised to a power. We can multiply the powers. Think of this as x to the fourth multiplied by itself, 2 additional x to the fourths. So we have x to the fourth, x to the fourth, x to the fourth, which would give us x to the 12th. So 2 plus x to the 12th power. This and this are not the same. If we were to take the time to simplify all of this down, this would have multiple terms, whereas this expression, this composition, only has 2 terms. So even though they were made up of the same functions, because we compose those functions in different orders, the resulting composite functions will not be the same. Okay, let's try another example. 2 different functions, and again, the goal is to compose them together in both orders. So here f of x is a square root function, and g of x is linear, x minus 1. We want to find f composed with g, and then g composed with f. So f composed with g, again remember that means we're taking the function g of x, whatever that happens to be, and we're making it the input for the function f. So we know that g of x is linear. It's defined as x minus 1. So this is going to be f of x minus 1. And then the rule for f says take your input, whatever it is, and take the square root of it. So we're going to take the square root of this particular input, x minus 1. So that's going to simplify to the square root of x minus 1. Keep in mind we can't go any further with this. You cannot split up a square root across addition or subtraction. So this will be the simplest form of this particular function. Now what if we compose in the opposite order? So this would be take f of x and make it the input for the function g. So f of x is defined as the square root of x in absence of any specific input. So g of the square root of x. And again, the rule for g says take your input and subtract 1 from it. So we're applying that to this particular operation, to this particular input. So square root of x subs it in, minus 1. Now notice these two are a little bit closer in terms of what they look like than the previous two functions we ended up with. But because the 1 is inside the radical, it's part of the radicand, what we call the radicand, here the 1 is outside of the square root. So essentially we have all of the same operations listed, but they're in the opposite order. So for instance, if you were to plug in an x value here, you would first subtract and then take the square root. Whereas if you were to plug in an x value here, you would take the square root first and then you would subtract. So we have the same operations, they would just be executed in a different order. But in general, these two functions are not the same. They don't represent the same function, again, because composition is not commutative. Okay, so just as functions can be composed, what we just did, we composed these functions together, functions can also be decomposed. You can reverse that process. They can be decomposed into two separate functions that are less complex than the original. So anytime we define an operation, it's good to be able to undo the operation. If we add, we can undo it with subtraction. If we multiply it, we can undo it with division. If we compose, we can undo it with decomposition. So essentially the general idea is, imagine if you started with this function. Imagine that was the function you started with. In doing a decomposition, what you're trying to find are the two original functions that you would have composed together to give you this function. You're taking this more complicated function and you're breaking it down into constituent functions, one that you're going to think of as an inner function and one that you're going to think of as an outer function. But notice these two individual functions treated by themselves are simpler than the function here that resulted from their composition. So the idea is we're going to take this more complicated function and we're going to break it down into simpler functions. We're going to decompose it. We're going to reverse the process of composition. Now when we reverse this, when we do the decomposition, we're looking for two specific things. Number one, an inner function, and number two, an outer function. The inner function is going to represent the innermost operations represented by that particular function, and then the outer function is typically going to take maybe just one operation, the outermost operations. Now sometimes you can look at a function and you can identify a clear inside and outside. So for instance, for this function, it's pretty clear that the square root is outside of everything else, and then x minus 1 is inside. So here we could think of this as being broken up into an inside function that just represents x minus 1, and then an outside function that just represents the square root. That would be a way to decompose. However, it's not always going to be intuitive how you would break it up into something inner and outer. So to be a little bit more formal about how we approach decomposition, identifying the inside, identifying the outside, what you want to do is consider the steps that you would take to evaluate the function if you were to plug in an input. In other words, look at all the operations represented in your function and think about how those operations would be applied based on the order of operations. That's going to tell you what's innermost and what's outermost and the order that all the operations would come in. So function 1, your inner function, is going to represent what you would plug into first. It's going to represent where you start, the innermost operations. So first, we're going to think of that as inner. And then function 2, our outer function, usually represents the absolute last operation that you would apply to simplify. In other words, the outermost operation. Usually the external, the outer function, will only have one operation, whereas the inner function is going to have all of the remaining operations, anything left over. So let's do a few examples with decomposition. For a lot of people, decomposition is kind of intuitive. For other people, this will be a challenge. So we're going to try to approach it as formally as possible, and then hopefully you'll start to get the idea about how things would be approached. Okay, so here's our function. This is a relatively complicated function. We have a couple of exponents. We also have something added on. So this is a layering of operations, one applied on top of the other. So what we want to find is an outer function and an inner function such that if we composed them together, g of x plugged into f of x, that would result in that more complicated function that we're starting with. So we're looking for that outer function and that inner function that we could then compose together to find this more complicated function. We're reversing the composition. So think of this kind of like the answer to the problem. We want to know what was the question. What were the two functions that we composed together to give this function? So to approach this in the most methodical way, I want to go through this function and I want to list out all of the operations that are applied to our variable and the order that we would apply them in, because we would apply them in a very specific order based on order of operations. So the very first operation we would apply to our x. So imagine you plugged in a value for x. Picture maybe plugging in a 0 or plugging in a 1, whatever you want. What's the first thing you would do to it? Well, you would have to square it. So the first operation you would apply is the exponent of 2. Okay. Now after you applied that exponent of 2, that would be simplified. You then have two operations left. You have a cube and you have an addition of 1. Because the square and the addition are inside parentheses, they apply before the cube is applied. So x squared would come first, and to that result, we would then add 1. So the second operation would be to add 1. And that would then give us everything in parentheses. We would take the result of that, and then we would cube it. So the third thing we would apply is the exponent of 3. So if we were to analyze inner versus outer, this is the innermost operation, and this is the outermost operation. So in decomposing this more complicated function, essentially what we want to do is write two separate functions that are going to break up this three-step process into smaller sequences of operations. So f of x is going to be our outer function, and in most cases we're only going to take the outermost operation and represent that as f of x. So I'm going to divide up the list here. The outermost function, or the outermost operation, will be associated with our outer function. So the outer function, f of x, is just going to be the function that would represent applying an exponent of 3 to our input. So keep in mind, although this function has a cube applying to all of this, we want to write a function that represents only applying an exponent of 3, not applying any of the other operations, just applying an exponent of 3 to our input of x. So the way we would write that would just be take the input, whatever it is, in this case it's x, and just apply an exponent of 3. In other words, just cube it. So that's going to be our outer function. The inner function is going to take everything that is left. So what's left is an exponent of 2, an addition of 1, in that order. So imagine taking your input and applying these two operations in that particular order. So you would take your input, which is x. To it, we apply an exponent of 2, so we're going to square it. And to the result of that, we're going to add 1. And so that would be our inner function. Now, the good news about a problem like this, even if this problem is relatively challenging to you, you can check your work. If you go back and compose these two functions together, you need to verify that the composition of these two functions, f composed with g, in other words, g of x plugged in to f of x, that should evaluate to the function you originally start with. So let's check that. So f composed with g of x is the same thing as f of g of x. Well, based on the g of x that we wrote, that's going to be f of x squared plus 1. Okay? And then the rule for f says take your input, whatever it is, and cube it. So in this case, we're cubing x squared plus 1. So that's going to be x squared plus 1, our specific input, cubed. And the only thing that's different from the original function is x squared plus 1 is written in that order rather than this order. But addition is commutative, you could flip the order, it doesn't matter. So because the function we got from the composition matches that original more complex function, this decomposition is going to be correct. That verifies that decomposition. Okay, let's try another one. Okay, in this case we have a square root of 3x squared minus 4. What's the inner? What's the outer? How do we layer it into two separate functions that could then be composed together to give us this more complex function? Let's see if we can do it maybe without making the list. Let's just go through it verbally. So imagine plugging in an x here. Okay, what would you do to simplify the expression once you plug in an x? Well, first thing you'd have to do is square it, so that would be the first operation. You'd take the result of squaring, multiply it by 3, so that would be the second operation. You'd take the result of that, subtract a 4, so that would be the third operation. And then all of that simplifies, and then you take the square root. So the square root in this case is the fourth, the final, the outermost operation. So using what we did here, the example we just demonstrated here, think of your outer function, f of x, as just representing the outermost operation here, the final operation we would apply. Well, in this case, the final operation we would apply is that square root. That's the outermost operation. So in writing f of x, I want to create a function that just represents applying a square root to your input, whatever your input happens to be. Here our input is x, so the function that just applies a square root to our input is going to be the square root of x. Our inner function has to take care of everything that's left over. So the remaining operations in order, we square, we multiply by 3, we subtract 4. Basically imagine removing the square root, what's left? Everything else has to be included as part of the inner function. So that's going to be 3x squared minus 4. If you were to compose these, g of x plugged into f of x, That would take this x, we'd sub in 3x squared minus 4, and so we'd have the square root of 3x squared minus 4, which is our original function. So this would be a decomposition we could use here. Let's try one more. Now this one is a little bit different. It's not as obvious. I'm going to start by rewriting this in a slightly different form. Remember the rule with exponents in the denominator? We talked about this. What does something in the denominator mean in terms of an exponent? What's another way of writing that? Well, remember, an exponent in the denominator could also be written as a negative exponent. So for instance, 1 over x squared is the same thing as x to the negative 2 power. And we know when we take a derivative, typically we would want to write it as x to the negative 2 rather than leaving it as 1 over x squared. When we use the power rule, that was what we typically did. So let's rewrite this using that particular technique. Now notice it's not just x squared, it's some other stuff squared. We have 4x plus 5 squared. But because we're taking some expression and squaring it, but that's in the denominator, well, that's going to be the same thing as taking that expression and raising it to the negative 2 power. Same kind of thing. And in this case, the expression we're applying that to is 4x plus 5. We've now essentially eliminated one operation. So this particular form involved a division. Here, we don't have division represented. The division is implicit in that negative exponent. But now we're in a better form to be able to decompose. So again, think about the order of operations in which you would apply each of these steps to an input. So imagine plugging in a value for x. How would you simplify this expression? Well, you'd multiply by 4. You would take the result of that and add 5. And then you would take that whole value and raise it to the negative 2 power. So the negative 2, the exponent of negative 2 is the outermost operation. So our outer function is going to be the function just representing the application of this exponent to whatever input we have. So it's going to be x to the negative 2 power. The inner function, g of x, is going to take care of everything else. So we have to multiply by 4 and add a 5 in that order. Basically think of everything that's inside of the exponent in this expression. So our inner function would be 4x plus 5. And again, imagine composing these together. F composed with g means take g of x and plug it into f. So take g of x, plug it in place of the input for x, and we would have 4x plus 5 raised to the negative 2 power, which again simplifies here if we don't use that negative exponent. So that gives you a sense of what decomposition looks like. Now, keep in mind, we have not taken any derivatives yet. But the idea is that if we have a more complicated function where we have operations nested within other operations, decomposition is where we're going to start before we take the derivative. So what we call the chain rule, the rule that we're going to use to differentiate these kinds of functions, is going to require that we start by finding this decomposition, by taking this more complicated function and breaking it down into these simpler constituent functions, the inner function, the outer function. Okay. So we're going to use the chain rule to differentiate all these more complicated functions by, again, first considering how they would be decomposed, into inner and outer functions. So suppose we have a composed function that results from composing f and g. So just to be clear, f is the outer function, g is the inner function. If we want to differentiate a composed function, so what are we doing? We're taking the derivative with respect to x of some function that's represented by a composition. Again, remember this notation means g of x is plugged in to f of x. It's going to be a layering. Okay, so here's how it's going to look. We're going to take the derivative of f, but rather than taking the derivative and just saying f prime of x, we're going to take the derivative, but that rule for the derivative, the formula for the derivative, we're going to sub in our inner function g of x. We're going to replace that generic input in our derivative with our inner function g of x. So differentiate the outer function and then take the rule you get when you differentiate that and plug in the inner function to that derivative. And then we're going to multiply by the derivative of the inside function. So as with the product rule, as with the quotient rule, there is very much a layering effect here. We do have to find the derivatives of the inner and the outer function, our constituent functions, but how we use them is going to be a little bit different. So here, our bookkeeping, staying organized, being very careful is going to be very, very important, because notice we're taking a derivative, but we're not using the derivative as it stands. We're using the derivative with something else substituted in place of x. So we're going to do several examples. We're really just going to focus on examples from here on out, because the chain rule is typically the hardest for most people to apply, just because there's so many layers to applying it. Number one, you start with your more complicated function. You have to decompose it, and then you have to apply this derivative rule. Now we're going to use the functions we already decomposed. So that part is going to be done for us. So h of x is equal to 1 plus x squared cubed. So this was the first function we decomposed. So let's go back and look at that decomposition. So we decomposed it into an outer function, x cubed, and an inner function, x squared plus 1. So I'm going to write my outer function and my inner function over here to the side. So f of x was defined as our outermost operation, the function that just applies that. And then g of x was defined as everything left over inside. So that's going to be 1 plus x squared. Now I need to differentiate each of these functions with respect to x. So f prime of x, it's going to require the power rule. So that's going to be 3x squared. Okay, and then g prime of x, we differentiate 1, that goes away. Okay, and then we differentiate x squared, that's going to be 2x. So we have 4 parts here that we can use. Are we going to need all the parts based on the derivative rule? Well, let's see. We need f prime, so we have f prime. We need g of x, we've got that. And we also need g prime of x. So notice what we don't need now that we've found these individual derivatives. Nowhere here in this formula do we see f of x. So I'm going to cross that out so we don't accidentally use it where we shouldn't. Now what else do we need? We have g prime of x as is, so we don't have to do anything with that. But notice here the derivative for f prime. Into that we're going to substitute g of x. So g of x is going to be plugged in to our derivative f prime of x. So where I see an x here, I'm going to substitute in the expression for g of x, and that is going to give me my derivative. So we're chaining things together. We're linking together a derivative with one of the original functions. The derivatives are chained together with the original function, hence the name, the chain rule. So when we take the derivative of this composed function based on how we decomposed it, remember it's going to be f prime of g of x. So let's start there. So f prime, but in place of x, we're subbing in our expression for g of x. So f prime says square it, multiply by 3. We have to apply those operations to g of x, in this case 1 plus x squared. So that's going to be 3 times the quantity 1 plus x squared squared, okay? So that's the derivative of f with g of x substituted in place of x. Now we're not quite done. We also have to multiply by the derivative of that inner function g of x. So we're going to multiply by 2x. And for all intents and purposes, that is the derivative, but we want to simplify as much as we can, ideally. Now, squaring here, we won't necessarily have to do that, but notice the 3 and the 2x. What we really have now are 3 factors multiplied together. 3 is a factor. 1 plus x squared squared is a factor, or we can think of it maybe as 2 factors, and then 2x is a factor. So these two things that are outside the parentheses can be multiplied together. Now you may be looking at this and thinking, well, why don't I just distribute the 3? You cannot distribute the 3 because everything in parentheses is being squared. Squaring takes place before you multiply. So distribution, the distributive property, does not apply here, not unless you went ahead and squared everything first. But we're not necessarily going to do that here because it's not necessarily going to make our derivative any simpler. We're going to find with the chain rule that we kind of sweep some things under the rug in terms of simplification, and there will be different ways to write the final expression for our derivative. But here, these two factors that are outside of parentheses, we can multiply those together. So 3 times 2 is going to be 6, and we'll attach the x to that, and then we can write what's left in parentheses. And so we're just going to leave it like that. That's fully simplified for our purposes. Of course, we could square this binomial. We could distribute the 6x if we want, but it's going to be acceptable to leave it in a form like this for the time being. Okay, let's try another one. This was the next one we decomposed, the one with the square root. So let's go back and look at that decomposition. So our outer function just took that outermost operation, the square root, and our inner function represented all of the other operations, in this case 3x squared minus 4. So just like with the previous example, let's write out those individual functions. So f of x is equal to the square root of x, and then g of x is equal to 3x squared minus 4. So now we want the derivatives of our individual functions. Now the square root, remember we don't have a rule for square roots, so we're going to write that with a fractional exponent, with an exponent of 1/2. So when I take the derivative, I'm going to use the power rule with that fractional exponent. So bring down the exponent and then decrease the exponent by 1. 1/2 minus 1 is negative 1/2. Now evaluate g prime of x. Bring down the 2. 2 times 3 is 6. Decrease the exponent by 1, and that's going to be x. And then differentiating the constant, it goes away. Okay, let's revisit the chain rule. So we need the derivative of the first function, we have that. We need the second function, we have that. We need the derivative of the second function, we have that. So at this point, we no longer need that original outer function. Now into the first derivative, we're substituting that inner function g of x. So g of x is going to be plugged in to our inner function, or our outer function's derivative. And then we're going to multiply the result of that with g prime of x, which is 6x. So let's put all that together. So h prime of x is going to take our outer function's derivative, so 1/2 times our input raised to the negative 1/2, but we're applying that sequence of operations to the inner function as an input. So where I have an x, I'm going to put parentheses and I'm going to sub in g of x. So 3x squared minus 4, and that's raised to the negative 1/2. And then we're going to take the result of that composition, that's a composition, that's f prime composed with g, one function plugged into the other, and I'm going to multiply that result by 6x. Okay, now as with the previous one, we have parentheses raised to an exponent, and we have a constant out front. And as tempting as it is to distribute it, you cannot distribute into parentheses that have an exponent other than 1. So leave your parentheses alone. Just focus on any factors that are outside parentheses. We can combine those together. So 1/2 times 6 over 2, that's going to be 3. And then we have 3 times x, that's multiplied by everything in parentheses, 3x squared minus 4 to the negative 1/2. Now remember, the negative means something, the 1/2 means something as well. Let's see if we can simplify both of those at the same time. Apply each of them. So the negative means we're going to take everything that exponent applies to, which is just what's in parentheses. Keep in mind, that exponent does not apply to 3x. It only applies to what's in parentheses. The negative says, take whatever's in there and flip it, take it to the denominator of our expression. Now what about the 1/2? The 1/2 is equivalent to a square root. An exponent of 1/2 is equivalent to a square root. So we're taking the square root of this expression, and the negative says take that square root and flip it to the denominator. Now what's going to happen to the 3x? You can think of the 3x as a 3x over 1, which means it's going to stay in the numerator. Again, the exponent does not apply to this. It's going to stay in the numerator. What's going to end up in the denominator is this expression to which this exponent applies. So the denominator because of the negative, and it becomes a square root because of that exponent of 1/2. So square root of 3x squared minus 4. And that's going to be our derivative. Okay, let's look at the last example based on what we already decomposed. And then we'll add on a little bit. We'll do a little bit more complicated examples. So let's revisit that decomposition. Okay, where is it? There it is, very bottom. Okay, so we ended up rewriting this a little bit first. We took that exponent that was in the denominator and rewrote this expression with a negative exponent so that we then have a function where we know the power rule is going to apply. So x to the negative 2, this is going to be our outer function, and then our inner function is 4x plus 5. Okay, so the outer function, f of x, is going to be x to the negative 2, and then the inner function, g of x, everything else, 4x plus 5. Differentiate each of them. F prime of x, bring down your exponent, be careful that's negative. So negative 2 times x raised to the negative 2 minus 1 power. Be careful, it's not going to go to negative 1. Negative 1 would increase the exponent. We're subtracting 1 from the exponent, which would take it to negative 3. And then g prime of x, here the derivative of 4x is going to be 4. The derivative of 5 is going to be 0. So it'll be f prime of x with g of x plugged in times the derivative of g of x. So I no longer need f of x. So the derivative, h prime of x, is going to take my outer derivative, substitute in my inner function to that derivative, so negative 2 times 4x plus 5 raised to the negative 3 power, and then multiply by the derivative of that inner function, so times 4. And this is again very similar to the previous two examples in terms of how we simplify. Everything outside those parentheses with that exponent can be combined together, and again everything is multiplied. So negative 2 times 4 is going to be negative 8, and that is multiplied by 4x plus 5 to the negative 3. The negative 3 power, the negative again says flip it, take it to the denominator. If you think of negative 8 as being negative 8 over 1, that's going to stay in the numerator. and this is going to go to your denominator. So that's going to be negative 8 over 4x plus 5 quantity cubed. And again, depending on the situation we're in, we could simplify this. This would be 4x plus 5 times 4x plus 5 times 4x plus 5. It would take a while to simplify, but it's doable. Here, because that's not really going to do anything special for us, we're just going to leave it as is. So that gives you a few examples where we really just use the chain rule. Keep in mind we use the power rule, we use the constant rule, we use the sum and difference rule, but those we think of as more basic rules. Now there also may be situations where we need to use the chain rule with the product rule, with the quotient rule, where we have more complicated situations, one rule nested inside of the other. It's going to be a matter of just breaking it down, going step by step, and really thinking about the structure of the function. What sort of operations do we see there, and what rule is going to correspond to the operations that we have. So let's do a few slightly more challenging examples. Okay, so here h of x is defined as 3 plus x cubed raised to the 5th power minus 1 plus x to the 7th raised to the 4th power. So what's going on here? Well, we have something nested inside of something else, another thing nested inside of another thing, and then the result of each of those compositions, that's the term for that, is subtracted. So if we were to look at just the first part here, differentiating this would require the chain rule because it's something inside of something else. Differentiating this would require the chain rule. Again, it's something plugged into something else. But the results of that are subtracted. So this, the fact that these two terms are subtracted, means we're going to apply the difference rule as part of our derivative. Well, all the difference rule tells us is that we can look at the individual derivatives and just subtract those individual derivatives. So we want to focus on each one of these expressions one at a time, and then when we take the final derivative, all we have to do is use that difference rule, which tells us take the derivative of the first, take the derivative of the second, and just stick them together with subtraction. So we want to look at one at a time. So I'm going to label this as 1. I'm going to label this as 2. The more organized we can be, the better. So for part 1, we have 3 plus x cubed raised to the 5th power, and we need to differentiate that. So it's an algebraic expression nested inside of one additional operation, in this case raising to the 5th power. So if we wanted to decompose this into an inner function and an outer function, remember f of x is traditionally the outer function, g of x will be the inner function. We're cubing, adding 3, and then taking all of that as one unit and raising it to the 5th power. So the 5th power, that exponent, represents the outermost operation. So our outer function is a function that just applies the 5th power to whatever input we choose. The inner function is going to have everything else. So 3 plus x cubed. Now we need to differentiate these. So f prime of x is going to be 5x to the 4th, and then g prime of x, 3 differentiates to 0, so we differentiate x cubed, and that's going to give us 3x squared. The derivative of the outer function with the inner function plugged in times the derivative of the inner function. So we no longer need this function. So the derivative here is going to be 5 times our inner function, which is 3 plus x cubed raised to the 4th power. All of that multiplied by the derivative of the inner function, which is 3x squared. Okay, hopefully it's starting to become kind of formulaic what you do at that point. Everything outside can be combined together. So 5 and 3 can multiply together. 5 times 3 is going to be 15. And then we have that x squared. And then we have everything in parentheses raised to the 4th power. So let me box that in. That's going to be the derivative for our first term right there. Okay, repeat for 2. So we have 1 plus x to the 7th raised to the 4th power. Outer, inner, break it down. So here our outer function is just going to represent our input, whatever that is, raised to the 4th power, so x to the 4th power. And then our inner function is everything else. So 1 plus x to the 7th. Okay, differentiate them. F prime of x is equal to 4x cubed. G prime of x is equal to 7x to the 6th. You're probably getting pretty fast with the power rule at this point. So our inner function is plugged into the derivative of our outer function. We multiply by the inner derivative, so we don't need this function anymore. So when we put that all together, that's going to be 4 times our inner function raised to the 3rd power. So 4 times 1 plus x to the 7th raised to the 3rd power times our inner function's derivative, 7 times x to the 6th. Okay, combine everything on the outside, clean it up. 4 times 7 is 28, so 28x to the 6th, and 1 plus x to the 7th cubed. And just to reiterate one more time, why do we not go further here? Why do we not distribute? We don't distribute because each of these sets of parentheses has an exponent applied to it. The exponent is always applied in order of operations before the multiplication is. So if we wanted to distribute, we would have to actually execute the cubing and the raising to the 4th power, which we don't want to do here. So we're just going to leave it as is. So if we want to differentiate the whole function, h prime of x, well, it's one composite function minus another composite function. And so the fact that we're differentiating two things that are subtracted tells us we can take the derivative of the first, the derivative of the second, and just subtract those two derivatives. So h prime of x is just going to be the result from 1 minus the result from 2, which is going to be 15x squared times 3 plus x cubed raised to the 4th power minus 28x to the 6th power times 1 plus x to the 7th cubed. That will be our final answer. Now, could we do anything else here? Well, technically we have a greatest common factor of x squared. If we wanted, we could factor it out. But then we have parentheses inside of parentheses, and it's just going to be more complicated than it is now. It's not necessarily going to help us to do that. So we're just going to leave that as is. That will be our final expression for our derivative. So what we have here is essentially like a power rule kind of applied to an inner function, something like that. So notice what happens when we take the derivative. If you were to look at just the composite function and think through the composite function without really breaking things down, it's like bringing down the exponent in front of your input and then decreasing the exponent by 1. So bring down the 5, you have your input, and then decrease the exponent by 1, and then we multiply by the derivative on the inside. Sometimes you'll see this called the extended power rule. It's really just a specific case involving the chain rule, but sometimes we give it the name the extended power rule, this idea where you have a function then raised to a power and what that derivative ends up looking like. So let's look at another example using the chain rule in conjunction with other rules. Okay, we want to differentiate this function. Well, what's going on here? Well, we have a product. This is negative 5x. If you want, you could put parentheses around that. Negative 5x times 2x minus 3 quantity raised to the 4th power. So it's a product of two things. This is one function, this is another function, if you really want to group things. And the second function in the product, we would need the chain rule to take the derivative of that particular function. So it's chain rule inside of a product rule, because the product rule is going to be required in order to differentiate the whole function. But we know as part of the product rule we have to have derivatives of each individual function. So having the derivative for one of those original functions, well, that requires the chain rule to differentiate. So we definitely want to break this one down as well. So just like before, let's call this 2 and I'm going to call this 1. I want to start, nah, that's a bad idea. Let's not do that. Let's call this 1 and 2. Let's keep things in order. Okay, so just like before, we need to differentiate each of these and then put it back into the context of the product rule. So let's remember, what does the product rule look like? The product rule looks like the first function times the derivative of the second plus the second function times the derivative of the first. Okay, so we need each of these individual functions, 1 and 2, and we need their derivatives. So if we wanted to use 1 and 2 in prime notation, think of this as 1 times the derivative of the second plus the second times the derivative of the first. And this is not real notation right here, but just to be consistent, give you a sense of what we're really looking at, this is what we're looking at right here. So let's start with function 1. Function 1 is pretty simple. So negative 5x. Okay, well, if we want to take its derivative, we don't have to use the chain rule there. That one's pretty quick. So 1, and then take its derivative. Well, negative 5 times x. We have an exponent of 1, bring it down, the x goes away. So that's going to be negative 5. So we have two parts of our product rule. Now we go to the more complex one. So function 2 is 2x minus 3 raised to the 4th power. And so when we take its derivative, let's see if we can use that idea of that extended power rule like I explained at the end of the last example. It's an input, something, raised to the 4th power. So if we were to use the power rule here, we'd bring down our exponent and then decrease the exponent by 1. So bring down the exponent, decrease your exponent by 1, but here it's being applied to the input 2x minus 3. Now if we do that, remember we also have to take the derivative of whatever was on the inside. So the derivative of the inside function, the derivative of 2x minus 3, would be just 2. So multiply your 2 and your 4 together. Remember, we can't distribute the 4. There's an exponent there. Multiply the 2 and the 4. That's going to give you 8 times 2x minus 3 cubed. And so we have our 4 parts. Now we can put them into our product rule and get the derivative of the actual function. So when we differentiate this function, the product of two other functions, it's the first, which is negative 5x, times the derivative of the second, which is going to be 8, times 2x minus 3 cubed, okay, plus the second function, not differentiated, 2x minus 3 to the 4th power, multiplied by the derivative of the first, which in this case we lucked out, it was just a constant, so negative 5. Okay, can we do anything with this? Well, we can clean up each of these individual terms. That's not a bad idea, so let's see if we can do that. So negative 5x times 8, remember we don't distribute into parentheses, so 2x minus 3 cubed, That stays as is, but we can multiply and we can write that as one factor. So negative 40x times 2x minus 3 cubed. And then maybe just write the negative 5 out front here. Just so it's really in the appropriate order. So there we go. Now, alternatively, you could potentially leave it there, but there are also a couple of other things you could do here, depending. I want you to pay attention to each of these two terms. Think of each of these as an individual term. Think in terms of factoring. We have two terms. Anytime we want to factor something with multiple terms, a good rule of thumb is always start by looking for the greatest common factor, whatever these two things have in common. Well, what do these two terms have in common? They actually have a lot in common, believe it or not. So if we look at everything that's outside of parentheses, we have a negative 40x and we have a negative 5. Well, those two factors have a negative 5 in common. So we could potentially factor out a negative 5 if we wanted. So let's see how we could write that. So factor out a negative 5. So we're then going to have to write what's left just a minute, but we're not quite done yet. What else do these two terms have in common? Well, we have 2x minus 3 cubed and then 2x minus 3 to the 4th power. So the same factor, 3 of them here, 4 of them here. So they have 3 in common. They have 3 2x minus 3's in common. That is also part of the greatest common factor. So we could also pull out a 2x minus 3 cubed. So what are we left with? I'm going to use brackets here because there's going to be a little bit of stuff nested. Think about what's left over after you remove each of these factors from each of these terms. So from the first term, well, we pulled out the whole 2x minus 3 cubed, so that's gone. We also pulled out a negative 5. So what's left? Well, if we divide out a negative 5 from negative 40, we're left with an 8. And we didn't do anything with that x because it wasn't shared among those two terms. So we're left with an 8 and we're left with an x. Now what about the next term? We factored out the negative 5. Now because this term was originally negative and we factored out the negative, what we're left with is now positive. And we had 4 2x minus 3's. We were able to pull out 3 of them because there were 3 that were in common, but that means we have 1 left over here. We still have an additional 2x minus 3 left. And so we again can't distribute here, but notice this is now just a combining like terms kind of thing. We have 8x and 2x, so that's going to be negative 5 times 2x minus 3 cubed times 8x plus 2x is 10x minus 3. So which answer is right? Is it this one? Is it this one? Well, the answer is they're both right. It just depends on the situation we're in. Sometimes having a further factored form, this would be fully factored. This is take those two terms and pull out everything they have in common, write it in a fully factored form. This would be a fully factored form, whereas this form is not. Either of them would be considered correct. This just takes you a little bit further. So honestly, at that point, it's kind of up to you which one you go with. Just be aware sometimes we'd want to take it a little bit further. If for some reason you're working through your homework and it doesn't like this answer, maybe take it a step further. Look for whatever these two terms have in common. If they have something in common, well, factor it out and then simplify everything you're left with. But either of these two answers would be considered appropriate. Okay, let's try one last example. So we did extended power rule, which is, think of the power rule as being part of the chain rule. We just used the chain rule inside of the product rule. Now let's use the chain rule inside of the quotient rule. So here, very much, we have one function divided by another. So remember our rule for differentiating a quotient. The way to remember it is low D high minus high D low all over low squared. And again, that's about as formal as this is, but if it helps you get to your final derivative, then it's worth it. So this will be our high, this will be our low. So in using the quotient rule, we're going to have to find the derivative of the upper function as well as the derivative of the lower function. So we need to explore each of those individually. So I'll write high instead of 1. Okay. So our upper function is 7x squared. And so d high, if we take the derivative of that, is that 7x squared? Excuse me, that's cubed. Let's fix that. There we go. That's 7x cubed. Okay, so the derivative of 7x cubed, we use the power rule, bring down the 3, which is going to give us a 21 out front, and decrease the exponent, so it'll be x squared. Now, the lower function, that's going to be 4 minus 9x raised to the 5th power. So this is a chain rule situation, or again, we can call it the extended power rule because it's really something raised to a power. Use the power rule, but multiply by the derivative of whatever happens to be inside of that exponential expression. So d low, the derivative of the lower function. Extended power rule says bring down your exponent. Forget about what's inside for a moment, but bring down your exponent. Then you have whatever raised to the exponent minus 1, so 4th power. But in this case, that's being applied to 4 minus 9x. And then, of course, because it's not just an x, because it's something else inside, we multiply by the derivative of whatever's on the inside. So the derivative of 4 is 0. The derivative of negative 9x is negative 9. Watch your signs. Be careful. Remember, you need that negative. And so if we multiply the 5 and negative 9, that's going to be negative 45 times 4 minus 9x to the 4th power. So we have the upper function, we have its derivative, we have the lower function, we have its derivative. So now we can put all of that into the quotient rule. So low, which is 4 minus 9x to the 5th. H prime of x, low, 4 minus 9x raised to the 5th power. D high, 21x squared, minus high, which is 7x cubed, d low, which is negative 45 times 4 minus 9x to the 4th, a lot going on here, divided by low squared. So 4 minus 9x to the 5th, and then square that. So I would put brackets around it. So 4 minus 9x is in parentheses. That's raised to the 5th power. But all of that as one unit is being squared. That is the derivative, but that is not the preferable form of the derivative. We want to clean this up. And think cleaning it up in terms of what we did here. Maybe not actually applying the 5th power or applying the 4th power, but looking for things that these two terms have in common. So this is one term, this is one term, each of them separated by subtraction. So look for the things they have in common. Now before you do that, it might not be a bad idea to just rearrange things, make things look a little bit better. Over here, we know we can multiply the 7 and the negative 45. So take care of those things before we start to look for anything to factor. So for the first term, typically we're going to leave whatever's in parentheses with its exponent out behind, and so anything else will be written in front of that. So 21x squared times 4 minus 9x raised to the 5th power. Okay, now over here, we have a negative multiplied by another negative. So that's going to give us a positive term. And then we have 7 times 45. So what's that going to be? Let's see. 7 times 45 is going to be 315. So 315. And we have an x cubed. And then we have the 4 minus 9x to the 4th power. Now what about the denominator? Well, we don't really want to raise this to the 5th power. Again, that's going to be a lot of work, and as it turns out, it's not going to be something we want to do here anyway, for a reason we'll see in just a minute. However, exponent raised to another exponent, we can simplify that. So power to a power, we multiply the powers. So that's going to be 4 minus 9x raised to the 10th power. Okay, so now each of our terms, let me highlight those again. So that's one term, that's another term. Each of these terms is about as simplified as it can be without actually applying that 5th power, that 4th power. So let's repeat what we did in the previous example. Now we're looking for anything that could be factored out, things that are common to these two terms. So let's start with everything that's outside of parentheses first. Well, we have an x squared here and an x cubed here, so there's two x's in common. Now what about the coefficients? So 21 and then 315. Well, we determined that 315 was the product of 7 and 45. We know 7 divides into 21. Is there anything else that might factor out? Well, let's see. So 315, does 21 go into 315? 315 divided by 21? Well, sure enough it does. So the greatest common factor there is actually 21. So 315 has a factor of 21. 21, of course, divides into itself. So let's factor that out. So 21 factors out. And then again, we have an x squared in common between that x squared and x cubed. So that can factor out as well. Now, what about the parentheses? Notice just like the one above, we have the same thing in parentheses, just raised to different powers. So we have 4 minus 9x's here. We have 4 of them here. So these two terms have 4 of them in common. So that can also be factored out. So 4 minus 9x, and they had 4 of them in common. So we're going to factor out 4 of them. Now here in some ways is the hard part. What are we left with? Make sure we don't lose anything. So from our first term, we factored out the 21, we factored out the x squared, and we factored out 4 minus 9x 4 times. Well, we started with 5 of them. That means we have 1 of them left. So we have a single 4 minus 9x left. What are we left with over here? Well, we started with 315, we factored out 21, and we determined that 315 factor out 21 or divide out 21 leaves us with a 15. So plus 15. We factored out an x squared from an x cubed, so we're left with a single x. And then we factored out 4 minus 9x to the 4th power out of 4 minus 9x to the 4th power, so we don't have anything left there. So there we go. And then all of that is still divided by our denominator, 4 minus 9x to the 10th power. Now I'm going to flip over, and I'll revisit this, but let's think through it before we flip over. What still needs to happen? Well, ideally we need to clean up everything here in brackets. So let's just start there, and then we'll determine what else might happen after that. Okay. And again, keep in mind, after we apply the quotient rule, we have the derivative, but it's not the preferred form of the derivative. We always want our algebraic expressions to be as simple as they possibly can be. So at this moment, we're just going and simplifying everything that's left over and putting it in a preferred form. So what were we left with? Well, we had we had 21x squared 4 minus 9x to the fourth. 21x squared, 4 minus 9x to the fourth power. And then the goal in this step was to clean up everything that was inside the brackets. So we have 4 minus 9x plus 15x. So negative 9 plus 15 is going to give us, what, 6? I'm having a moment. Negative 9 plus 15, 6. That's sad. You can do calculus and you can't do arithmetic. So we have 6x and 4. So positive 6x plus 4. And then all of that is divided by, we had 4 minus 9x to the 10th. Now I notice here these still have a factor of 2 in common, which means I didn't get the whole greatest common factor. If we want, we can still factor out a 2. But before we do that, forget about these for a moment. Look what we have there in the middle. We have 4 minus 9x as a common factor in the numerator and in the denominator. That ultimately is the benefit of doing all this factoring. Because we have a rational expression, we have the potential to cancel things in the numerator and denominator as long as we have common factors. Well, we have 4 of these in the numerator, and we have 10 of them in the denominator. So we can divide out the 4 they have in common, which will leave us with 6 of them in the denominator. So let's rewrite what we have left now. So 21x squared, all 4 of these factored out because they canceled with what was in the denominator. So we still have 6x plus 4 divided by 4 minus 9x to the 6th power. And again, it looks like I didn't get the whole greatest common factor because 6 and 4 still have something in common. They still have a 2 in common. So let's factor that out as well. So if I factor out that 2, I now have 21 times 2, which is going to be 42. I have my x squared. And then when I remove that 2, 6 divided by 2 is going to be 3, so 3x. And 4 divided by 2 is going to be 2. All of that divided by 4 minus 9x to the 6th power. And that is going to be our fully simplified derivative. So just to recap what happened with this one, this was a long one. The actual function itself that we started with was a quotient of 2 individual functions. So we had to use the quotient rule to differentiate. Now within the quotient rule, we needed the derivative of the upper function, the derivative of the lower function, but the lower function required the use of the chain rule. In this case, we can think of it like the extended power rule. So take the derivative of the outside, so 5 times whatever, raised to the 4th power, plug in whatever, which is 4 minus 9x in this case, multiply by the derivative of the inside function. So the chain rule was used inside of the quotient rule. Past that, it was honestly just algebra to simplify it. So again, once you get to this point, this is technically the derivative. It's just not a fully simplified version. So we went all the way from something that looks like that to something quite a bit simpler, at least in terms of length. So once we have the chain rule mastered, that essentially takes care of almost any function we could end up with. There are a couple of special cases where we'll need an additional rule, not necessarily to deal with a structural kind of issue, but to deal with a couple of specific operations. So specifically, if we have an exponential function, or if we have a function that has a logarithm. We don't have rules yet to deal with those, so we will have a couple of additional derivative rules that will allow us to differentiate those kinds of functions. But once we have the chain rule, combined with the product rule, the quotient rule, our sum and difference rule, and our power rule, that pretty much allows us to differentiate anything we want.